Now we'll start our last set of notes, which is on applications in business and economics. So in this set of notes, we aren't talking about any new techniques. So we won't be talking about things like integration by parts or any new integral techniques. Instead, we're just sort of seeing some applications of the integral techniques that we've already built up. So there are actually a ton of applications of calculus, and unfortunately we won't be able to really get into them. We're going to focus on two of them in this lecture. So I will talk about those in a bit, but before we actually get started on the notes, I want to show you how to integrate something that looks like this in sort of a shorthand way. So maybe let's just look at a concrete example where r is equal to 7. So let's say that you're trying to integrate e to the 7t dt. So what we would do is we would do a u substitution here. So I would take u to be 7t, and then du would be 7 dt. And remember that in a u substitution, we're trying to take the original integral and rewrite it exclusively in terms of u and du. So this first part I could write as e to the u dt. We're not done because this integral still needs to be written in terms of just u. So I could solve this equation for dt. If I did that, I would divide both sides by 7 to get that du divided by 7 is equal to dt. And that means that I can just plug in that dt value into this integral over here. I would get the integral of e to the u du over 7. Or if you want, you could factor out that 1/7 and put it in front of the integral. That would be 1 over 7 times e to the u du, and we integrate that. And now, if you integrate e to the u du, you would just get e to the u. So this would be 1/7 e to the u plus c. And then if you want to clean this up a little bit, you can. So u is 7t. So I can plug that in. This would be e to the 7t divided by 7 plus c. So the thing to notice here is that ignoring all of the middle steps, what we started with was the integral of e to the 7t, and what we got as our antiderivative here was e to the 7t divided by that 7. So when you have something like e to the rt and you're integrating it, pretend that this r is a constant, then if you integrate e to a constant times your variable, what you'll get is the same exponential expression divided by that constant. So here we were dividing by 7. In the generic case, we'll be dividing by whatever constant is sitting next to the t here. So this will be e to the rt divided by r plus c. So that gives us sort of a general formula that I'll be using several times throughout this set of notes. But you can always justify that formula by using this u substitution like I did here. Okay, so now let's look at the first set of notes here. The first part of this set of notes has to do with computing things like total income, future value, and present value for a continuous income stream. So in Math 1324, if you took it, the business algebra math, what we talked about was how to compute things like the amount of interest that you would get from an account if you made a single big deposit and then allowed it to accumulate interest compounded continuously. So here we're going to finally be able to talk about how to compute the amount that lives in an account if you have some continuous rate of flow. So let's say that you have some yearly salary that's going to be deposited into your account continuously over the course of the year rather than in one lump sum. In that case, you would need an integral in order to compute things like the total income that you would get or the future value after some amount of time. So I'm actually going to change to blue. There we go. So the nice thing about this first section here, or really this entire section of notes, is that it's usually going to be obvious which one of these formulas to use. So if you just want the total income from some income stream, and f of t represents the rate of flow for that income stream, then the total income that you would get is just gotten by integrating that rate of flow from your initial time to your final time. And then similarly for things like the future value or the present value, we're just going to be integrating that f of x, which is the rate of flow, against some exponential term. So this is actually a typo. This should be f of t. So we want to be integrating this f of t against some exponential. That exponential term depends on whether you want to be computing the future value or the present value. I think I'll talk more about these as we get to examples with them so that we aren't just staring at formulas. But I want you to keep referring back to this page as we go through the examples so that you can see which formula we're using and why. So let's first just look at example 1. It says the rate of change of income earned from a certain arcade game is given by this f of t function, where t is the time in years since the installation of the game. Find the total income produced by the game during the first 3 years of operation. So I want you to have that formula sheet in front of you so that you can see how we're applying those formulas. But here the key word is that we're finding the total income. So if you see that phrase, you know we're using this total income formula, which says that you should integrate from the initial time to the final time the flow rate. Now in this case, we're starting at time 0 and we're going through the first 3 years of operation. So we're going to be integrating from 0 to 3, and we're integrating f of t dt. This will be the integral from 0 to 3 of 6,000 e to the 0.05 t dt. And this is why I wanted to talk about the integration of exponentials that look like this. Oops. So if I want to compute this definite integral, I need to find the antiderivative of this expression. And to find the antiderivative, I know that that constant factor is just going to stick around. So I have a 6,000, and then I will have the exponential term divided by that constant in the exponential factor, in the exponent. So this is what I'll get as my antiderivative, and then remember we need to evaluate that antiderivative from 0 to 3 because those are our integral bounds. So we would end up getting the antiderivative evaluated at 3. So I would plug in a 3 for t, minus the antiderivative evaluated at 0. Notice that in this case, the antiderivative evaluated at 0, this expression, is not equal to 0, because here we just have an exponent that's equal to 0, and that would cause e to the 0 to just be 1. So if you plug this into a calculator, what we end up getting is $19,420. So that's the total amount of income that they would get from that particular machine. So again, I think the nice thing about this section is that there really won't be any tricks in terms of deciding which formula to use. It should be obvious which formula to use just based on the phrasing of the original problem. The phrasing of the problem will always include things like total income or future value or present value, and that will tell you which one of these formulas to use. So I think of this section as just being sort of a formula application section. You choose the correct formula, and then you compute the corresponding integral. So let's look at another one like that. So here it says if you have a continuous income stream modeled by this function, where t is time in years, what will your total income be after 6 years? So we know that the total income formula says that the total income is the integral from the initial time to the final time of your rate of flow. And here we're going over the course of 6 years, so that would be starting at time 0 and going up to time 6. And we know that f of t is 1200 plus 5 e to the 0.02, oops, just 0.2 t. So that's what we want to be integrating First, let's compute the antiderivative. So the antiderivative of 1200 is going to be 1200 times t when we integrate it with respect to t. And then I need to add the antiderivative of this term. So when I take the antiderivative of this term, I would keep the 5, because that's just this constant factor. And then the e to the 0.2t, when I integrate that, I'll get e to the 0.2t divided by that constant, which is 0.2 in this case. So that's my antiderivative. And I need to evaluate this from 0 to 6. So what I would get is 1200 times 6 plus 5 times e to the 0.2 times 6 divided by 0.2. This is all just the evaluation at 6. And then I need to subtract the evaluation at 0. So that would be minus 1200 times 0 plus 5 times e to the 0.2 times 0 divided by 0.2. If you just plug in 0. And you could obviously clean this up quite a bit, but it's okay to just plug this entire expression into your calculator. The main thing that I want to point out, though, is that this minus sign that occurs between your evaluations, it applies to the entire evaluation at 0. So this minus sign would need to distribute if you were to compute the rest of this by hand. So we'll have the entire evaluation at 6 minus the entire evaluation at 0. If you plug that into your calculator, what you'll end up getting is 7258 even. So this would be the total income from that particular income stream over the course of 6 years. And these models are going to be relatively accurate for any sort of regular deposits, but they get more and more accurate the more frequent the deposits are. So for example, maybe let's look at problem 3. Here it says a 25-year-old places a continuous stream of $4,000 per year into a retirement account which has continuously compounding interest at a rate of 1.5%. What will be the value of this continuous stream when this person reaches the age of 65? So here the rate of flow is 4,000 per year. So f of t in this example is going to be 4,000. That's our rate of flow per year. Now, if this were just deposited in one big chunk each year, so if it was just a single deposit of $4,000 per year, then this model wouldn't be super accurate. But if we're depositing the $4,000 evenly over the course of, 12 months or 365 days, then this model gets more and more accurate the more deposits that you make. So this is describing the total flow over the course of the 1 year, but these models get more and more accurate depending on the number of individual deposits that you'll make. So you should sort of imagine that you're making daily deposits that will total up to $4,000 over the course of the year. Okay, so I think I will do this video, I'll do this example in the next video, just so that we can look back at the formulas up at the top before we start on this one.